Thank you so much, Lance, for that kind intro. And I just want to say thank you for the amazing opportunity to come here and join you at this wonderful venue and at this wonderful event. Thanks very much to Connie, to Mrs. Bush, to Lori, to Meredith, and the Texas Tech team, as well as the Laura Bush Institute. I am just amazed at the amount of work and the amount of good that this institute has done over the years. And so when Connie actually, contacted me and said, hey, do you want to give this talk on cancer vaccines? Well, I work on cancer vaccines, so my inclination was yes. But more importantly, I thought, wow, we're coming out of a pandemic, all this stuff going on in the world. What an awesome opportunity to talk about something that gives some hope. Right? That will leave you at the end of the day with perhaps what I wake up with every morning, which is a wonderful opportunity to try to make a difference and make people feel better when they're down and out. Right? So I'm going to hopefully take you through the journey of cancer vaccines. Right? This is a field that is absolutely exploding now. When I first went into oncology, for instance, melanoma patients, if they're disseminated, this was a death sentence. Response rates are 1%, if that, with highly toxic therapies. Nowadays, with immunotherapies, which I will take you through the development of, we see that the response rates are greater than 50%. And it was just published that the 5-year survival tops 50%. When I was at Memorial Sloan Kettering in New York, we just ran a trial, a phase 1 trial, where combination immunotherapies have now resulted in kidney cancer response rates of greater than 90%, whereas previously this was 1%. We live in a time, I want to impress upon you that we live in a time where these medical breakthroughs are happening, some of which are in the media, some of which are not, but I wanted to make sure you knew that these advances don't come around but once every 1 or 2 generations, and we're living through that. And so I'm going to try to put what I'm going to talk about into context. Hopefully this can help folks that you may know to receive some of this information, as well as the Institute for helping spread the education. So vaccines. All right, so what are vaccines? Vaccines generally are a relatively easy way to reprogram your immune system, right? And this concept has been around for over 100 years. In terms of cancer vaccines, and I don't have a pointer, so I'm going to go ahead and just say left and right on the slide. On the left side, you see this gentleman in the 1800s, William Cooley. This was a physician that was a prominent physician at the time, at the turn of the century of the 1800s, who thought, okay, can I treat cancers with infections? And what William Cooley did was actually he injected sarcomas, these tumors of the soft tissue and muscle, with bacteria. And it was pretty crude at the time, and but amazingly enough, some folks actually responded. And he treated the daughter of one of the original Rockefellers, and her tumor shrunk. And now there were problems. Not everybody responded, and if you just put bacteria, then there are other issues. But the concept was actually demonstrated that the immune system and cancer talk in the same language. Okay, and that the immune system can be used to fight tumor cells and cancers. And now you fast forward more than 100 years later, you see that in 2013, with the advent of some new agents that are on the scene now that are available to everybody, like the different immunotherapies, immune checkpoint blockades, anti-PD-1, if you may have heard about this, that made the breakthrough of the year for cancer immunotherapy in Science magazine. And since then, this has spawned a Nobel Prize and multiple past Nobel Prizes of formulating the basis of all of this. And so what does this involve? Well, the immune system is designed through evolution to help us get rid of what is not supposed to be there, okay? So it fights what I call non-self. If you get a cut, for instance, if you undergo surgery, if you have a wound. It is the army of cells in your body that allows you to fight off infection and disease. But what a lot of people don't know, and honestly, only in the last 10 years have we really understood this fact, that it is also responsible for fighting non-self that comes from inside. If you smoke, it can cause mutations. If you have HPV, it can screw up the cells in the cervix and head and neck. And these become, in essence, partly foreign. They're not supposed to be there. And it turns out that the immune system has evolved over many eons to actually allow us to fight some of these things as well. And so this is what I put here. And some of these slides, I'm going to try to take you through the journey of all this and talk about a little bit about the science, but give you a little bit of grounding in the basis of vaccines. So again, on the left, if you get a cut, bacteria can come in, and it's very important for us to fight this off, right? So the immune system has evolved all these soldier cells to try to destroy these bacteria. Now, on the right side, you see that the threat doesn't necessarily come from outside all the time. It can come from inside, because our cells, we have billions and billions of cells, okay? And they are all dividing all the time. Dr. Baker actually mentioned very presciently that all our cells are dividing all the time, and viruses can screw them up. Too much sunbathing, for instance, can cause mutations. And these things can cause changes that make the cells more non-self. And so the immune system actually can fight off and help you prevent cancer. So it is very important to have a healthy immune system as a cancer preventative. It really is something that we have realized in the last several decades. And so the details are not important. This is just simply up here to show you that there are a bunch of different cells. In the media, we may talk about T cells, whether your T cells go up, or antibodies. There's a component of the immune system there that acts really quickly on the left. And there's a slow response immunity that kicks in once you get something like vaccines. That's where antibodies fit in, right? Like you hear in the media about antibodies and so forth, boosting the fight against COVID and other viruses. So there's a bunch of soldiers. It's very complex and it's running around it. But I want you to pay attention to things called the B cells and the T cells up here. Those are the primary general soldier cells that are out there that love to coordinate your response. You have to educate those B cells and T cells to fight off, to teach them what to fight off, right? And for cancer, these are not the typical bacteria that we see, right? Over the last 10,000, 20,000 years, the bacteria that we as human beings see in our environment, we've essentially figured out ways to fight these things off. But the cells that are in your body that arise, these are much harder. They're much more similar to self, okay, your own cells. They're slightly different. So it makes the immune system and these soldiers work much harder. And so sometimes you need to train these cells in order to fight off cancers or self cells more efficiently. So it turns out that the immune system is a wonderful way to do this, right? The immune system, now the terminology here is not important, but simply to say that it's a perfect cancer agent. The immune cells are designed to get rid of non-self, right? And what I list up there, T cells and antibodies with diversity, this is simply to just say that these T cells and B cells can generate many different modes of attack, right? These are all essentially drugs. We sort of, in the healthcare industry, celebrate if we make one vaccine and say, oh, that's fantastic. In any time in your body, you have 10 to the 18 different types of cells that are floating around that can help you fight off whatever. Right, so it is quite an amazing sort of system that we have, that we've been granted. And the timeline of immunotherapy, starting from William Cooley that I mentioned, it started years and years ago, over 100 years ago. And over time, there has been development both on the infectious disease setting as well as in the cancer setting. And over the 50s, 60s, 70s, knowledge has increasingly been gained over this time. And I think the main time period in which this thing really was hit out of the ballpark was in 2011, when the first immunotherapy was developed. And these types of immunotherapies allowed us, and they're antibodies actually, and they allowed us to be able to reawaken our immune cells and to fight off cancer cells. And for the first time, this drug is called Ipi in 2011. For the first time, we were able actually to really systematically activate the immune system against cancer. And this led to a Nobel Prize, and subsequently, very shortly afterwards, a drug called anti-PD-1 was developed, right? Now, these drugs also awaken the T cells. They activate the T cells and essentially take the blinders off and allow the T cells to go kill cancer cells. And you have seen some amazing results. Jimmy Carter, for instance, had a complete response. He was on, he was going to die. Okay, he had metastatic disease, complete response, essentially years and years free of disease now. And in my own clinic, I've had folks over 20 years that are out of therapy that have just done fine. Now, not everybody responds. This is a great baseline of development, for therapeutics for patients, but less than 50% of patients really benefit. And some diseases, patients with some diseases do much better than others. And so one of the things that I'll impress upon you is that in cancer therapy, there are two types of approaches. One type on the left really is where it's very complex, and it's meant to be, where folks will make a drug and try to target one specific protein amongst thousands and thousands of proteins. The immune system is much more elegant. The immune systems are these cells, as I put up there, that have developed over eons actually to help destroy non-self. Okay, that is what it does. More than that, it has memory, which means that you can train these soldiers that I talked about to really destroy things and keep destroying what's not supposed to be there for the lifetime of the patient, which is an amazing thing, because after a while, if you give a drug, people can become resistant, much like antibiotics for bacteria. So this is an example here of how this has impacted our field. All right, so on the left, you see the results of a patient of ours when I was in New York at the Memorial Sloan Kettering Cancer Center, and my colleague Paul Chapman, who's a melanoma doc, saw this patient who had metastatic melanoma. I mean, you see the scan there, and you see that lump there on the chest, which is what she had. She was in trouble. You remember, this thing did not respond to anything more than about 1% to 2%. She was given a single injection of Ipi-Nivo, and the entire disease disappeared, which demonstrates the power of the immune system. And on the right, what you see here is the general response rates. The graph is a little complex, but what you can probably appreciate is that across different cancers, patients get benefit, and as a single agent, the response rates roughly are around 20 to 30%. Not great, right? However, compared to the 1% or 0% previous to this was a game changer. And for patients that actually do respond, you see what can happen on the left, where you get these durable responses where you train the immune system to forever recognize those cancers and eradicate them, which is really what we're trying to do. So this is a little bit of a complex slide, but it's basically here to show you that there are a lot of things on the tumor cell side and on the immune cell side which actually need to happen. And these need to join in the middle, which is shown by the green box. And I want to introduce the concept of the epitope. Okay, the epitope is basically what a vaccine does. It is the spike protein epitope and others you've heard about. These things are the things that are in vaccines that train the immune system and T cells to help you fight off not only infectious diseases like HPV, but also cancers. And so you need that middle box actually to come together, and you need that orange dot to be correct. You need the right epitope or the right signal that allows the tumor cells to be seen. Okay, you can imagine it as your ID card. So some of our original work, which started over a decade ago, basically showed, and this is a little bit complex, but showed the concept that when a tumor cell has a lot of mutations, when it builds up all this damage from smoking or from UV light, these are the types of tumors that immunotherapies in general are most likely able to cure, all right? Because the more differences a tumor has, as shown up there on the top panel, the more likely it is for the immune system to be able to find one of those epitopes, remember those orange dots, to kill that cell. So this was a fundamental concept that was underlied a lot of the development of new cancer vaccines these days. And so what are these things? Well, these antigens or epitopes, they're called neoantigens, but what they are can be any protein in the body, right? They can be any protein, and when a protein undergoes a mutation, which happens in cancer, so cancers develop when you get mutations, what happens is that some of those proteins aren't supposed to be there. And so what happens is the immune system gets very angry. They recognize this as being foreign. Remember the concept of non-self, and it programs T cells to go ahead and attack, all right? And so the T cells go ahead and attack, and you get a rejection of the tumor cell. That's the whole concept of how vaccines work, including the HPV vaccine, including some of the new ones, which I'll tell you that have developed, that have generated some striking results. So how does this happen? Well, you get the shot, okay, and you get the right epitope there. It goes into the immune system, and remember what I said before, it shows the T cells and other types of immune cells what the right epitopes are. It identifies, it places the right ID on the right cell, which allows the T cell to then go kill that cell. That's how almost all vaccines work, okay? And in the setting of cancer, that is what is needed to help the immune cell kill the cancer cell, which again shouldn't be there. So what are the types of cancer vaccines? Well, there's preventative vaccines, which Dr. Baker talked about. These are Cervarix, Gardasil, and others, which help you prevent a cancer that can develop years later from a virus or from something that develops. And I'm going to go through some of those viruses that are approved and ones that are coming online. And then there's also therapeutic vaccines. And that is, these are vaccines which, when you have a tumor already or a disease, you already have an illness, they can be therapeutic. They reprogram the immune system to kill whatever type of tumor cells you have, including melanomas and others. And so these are some of the viruses that cause cancer. I'm going to run through these very quickly. Dr. Baker talked about human papilloma virus, of course. You know, it is just and she showed this already, but it is literally the #1 cause of head and neck cancer now, right? Which is amazing, because not so long ago, smoking was. Now smoking is no longer, the cause. Not only that, the rates are going up. So this affects everybody, both men and women. But there are other cancers as well where a preventative cancer vaccine can be important. Epstein-Barr virus for lymphomas and nasopharyngeal cancers. And recently, interestingly enough, Epstein-Barr virus has been linked to multiple sclerosis. Okay, so it turns out that long-term infection with EBV scrambles the signal of the immune system and eventually causes multiple sclerosis. How devastating is multiple sclerosis, right? So it's not just cancer, but it's a variety of other diseases that are caused by these viruses. And of course, many of you know about hepatitis B and C. These things, we as healthcare workers, we are required to get the hepatitis B vaccine, right? Because we're at increased risks. These things can cause liver cancers. And also things that are associated with AIDS, like human herpes virus 8, and also there's a rare skin cancer called Merkel cell disease, and MCV is the cause of this cancer. And so there's a lot that we're learning. It's important to understand that our environment is actually potentially increasing our risk for different cancers. And there will be more of these that are found over time. So this is simply just to reiterate what Dr. Baker had mentioned, that HPV has been a game changer, right? This is published from the New England Journal, and those lines are basically showing you the cumulative incidence of cervical cancer. And you can look at the green line up there, what happens when a population of patients are vaccinated successfully at 17 years or under. You actually eliminate this disease. This is the power that can happen, and why education is so important now, and some of the work by this institute is pushing forward, right? Because the challenges now are not simply that the technology doesn't exist. It does. It's around. It's been around for half a decade. It is really education on how one can think about these and make this more accessible and tackle disparities, right? Which is it's a big issue now. I'm going to talk a little bit about one of my patients here. Why are cancer vaccines important? Well, so this was very interesting. This was a 16-year-old girl with a skull-based tumor in our clinic, and she had a very aggressive head and neck cancer, and she was going to die. She had failed chemotherapy and so forth. And as a last-ditch effort, we went ahead and sequenced her tumor, and we found 12 mutations, and we found one of those successful orange epitopes, okay? And we went ahead and put her on anti-PD-1, and she had a complete response. And she was able to go to college, able to go to graduate school afterwards, and was able to maintain a cancer-free condition. And what you see on the top is her PET scan with some of her lesions disappearing. And we found that it was largely due. Now, the question is, okay, well, this doesn't happen in everybody, right? I wish everybody had these types of responses. So we did we scienced the heck out of this, all right? And we figured out that basically there was one of those epitopes that was responsible, that one in the red. And we scanned all the potential epitopes that could potentially be reactive to, and it turned out that anti-PD-1, which is really, as I said before, awakens T cells. It awakens many of the T cells, right? Turns out that one of them was responsible for causing her tumor to completely disappear, which is the one in the red. And it turns out that this has remained in her system all this time. Wouldn't it be wonderful if we could harness the ability to detect and use those types of epitopes for broad vaccines? That is the concept of cancer vaccine development, right? So I hope you understand that it is the ability to diagnose the tumor properly, to use a bunch of science and genomic sequencing to figure out exactly what is wrong, and to direct T cells to be able to fight off those specific ID cards, okay? That is what it's all about, right? And it is only possible because of the amazing advances in sequencing and basic sciences and clinical sciences that we all, as a society, has elected to invest in, right? In fact, one of the things I will say is, I know I'm not supposed to talk about COVID, but I'm going to just mention this one time. And that is the reason why these vaccines and monoclonals have been able to be put out so quickly was that prior to the development of these vaccines by BioNTech and others, all of these platforms were anti-cancer vaccines. COVID was not on the map. The reason why RNA and all these things were being developed was because phase 1 trials were already using them. We ran many of those trials ourselves. And so they were able to just swap out those little red bars, those cancer epitopes, and throw in the spike. That's why it was so fast. Without all this other basic research, we would be in a much, much worse position right now. And it is a testament to the fact that sometimes science and something beneficial to society may come from a completely different direction. And we have very hard time to actually predict. That's why I'm a big proponent, even though I'm a clinical scientist, of funding for basic science. And that is a huge, huge, huge thing endeavor. So as a Nobel Prize winner from Japan once said, we don't know what mountains we will need to climb tomorrow. Okay? So how does this work? This slide basically shows, as I said, is that when we get a patient gets a tumor, we sequence the tumor, and then we identify which of the little epitopes are important, and then we use those to develop a vaccine and give it back to the patient. Right? So that is the paradigm. And this is complex, but I just wanted to impress upon you what is involved, and that is a cancer patient will undergo sequencing. There's amazing genetics now. We can sequence the entire genome in one day now for about $1,000. And this has come down from the 90s. Actually, a lot of this started in the Bush presidency, actually, for the whole genome sequencing, right? The first genomes cost a lot of money. It was $500,000, took months and months. In our lifetimes, we have seen this now become a desktop assay. I have my own lab, a little box that can sequence your genome in a day, which is, to me, just mind-blowing, right? So this is what's being used, and the data is used to identify those epitopes, and those epitopes are used to actually develop vaccines. And so what are the platforms? Now, I put this up there just because there's a lot of information, on the media and so forth, RNA, virus vectors, AstraZeneca. What's the difference between all of this, right? All of these things. Well, RNA is a molecule which has been on the news. It's highly successful, and it is what encodes all the proteins. It's what tells the body what to make, right? So you can use RNA as a vaccine, and it's easier and it's faster to actually change the sequence and make. The classic ones, like the original polio vaccine, the flu vaccine, for instance, are peptides and proteins. Those are the classic ways to make ones. And it's harder to make those because imagine you have to grow up big vats of virus in order to make the vaccine. You can do an intermediate, which is a viral vector. You take like a harmless cold virus, you stuff in a peptide that you want your T cells to fight off, and then you can actually use that as a vaccine. So some of the original, polio vaccines, a Salk vaccine, the Ebola vaccine, for instance, actually makes use of that technology as well. So these are some of the next generation ones, right? So I promised to show, some of the ones that are on the horizon. This gets more and more advanced, and you may want to know about these two things. There are next generation adenovirus vectors, which are already currently being used in some of the different viral vectors, and there's something called self-amplifying RNA, where you can design these things to be a tiny bit of material you inject. You don't need all these big production processes. You don't need the freezers to freeze down, things down to -80. With self-amplifying RNAs, which are now exploding on the scene, you can take these to third world countries, Africa. They can be at room temperature, lyophilized into a powder and be given. So this is what is coming next. And as you know, I think one of the things that the pandemic has taught us that we can never take these things for granted, right? We live in a world where we are part of our environment, and we need to prepare ourselves, as I was talking about at dinner, for a potential next wave. I think we are much more prepared now, but with some of these different delivery vehicles, I think we'll be even more prepared. Some of us, including myself, were in efforts now to make pan-coronavirus vaccines, which would target 20 different places throughout the entire family to just basically boost immunity across all the viruses to make this just basically not a problem anymore. So I think that's where the field is headed. A lot of this technology is going to be re-engineered for cancer, of course. I'm going to go ahead and skip this. So these are some of the next generation approaches. You can use things like RNA, and you can use them in combination with self-amplifying RNAs together. When you use two different things together, they can drive up the immune response even more. I'm going to show you how this can work. So we're running phase ones, and I want to take a little bit of time to mention that despite the pandemic, it is very, very important to note that other diseases like cardiovascular disease and cancer do not stop, okay? We at the Cleveland Clinic, unfortunately, live in an area where there's a lot of, the smoking rates are still very high, and folks have come in with large tumors that are essentially uncurable. So, if you have friends out there to tell you, it's important to tell them that cancer screenings are still very important. These are critical, all right? But I mention this because these are phase ones that were done prior to COVID, and the cancer trial efforts stopped, rightly so, because we shifted towards COVID to get rid of that problem, and then we shifted back again recently. And what you'll see in the next 5 to 10 years, I think, is a massive doubling down on this. This is one of the first patients treated on our combination next generation platform. It's a little bit complex, but what you see here is you see one row being where this patient had metastatic lung cancer, week 8, week 16, and week 48. All right, and what you see in the blue arrow is that this woman's tumor has just disappeared. All right, so we sequenced the tumor DNA, we identified the epitopes, made it into a vaccine, and it just basically eradicated the tumor. This is another example. This patient had a large liver lesion from, I believe, a colon cancer. The most important part is actually at the bottom. You see a PET scan there. You see that area that's lit up? That's in the liver. That's the tumor. Big tumor, right? This thing covers essentially half the body. After some of our initial trial results and a personalized vaccine, you see that this thing has disappeared and she remains disease-free. So not everybody responds as well, but what we're seeing is some very, very powerful effects that are harnessed by the immune system. And this is simply up there just to show you that all those T cells, all those soldiers, previously they did not react against the cancer. Afterwards, you see that they all went up, all right? They all reacted against the tumor. And you see that patients, these are survival curves, that the patients that saw that blood markers for these cancers decrease after the vaccines lived a lot longer, right? And so these data now are in early phase ones, of course. It turns out that much of this progress happened literally months before COVID hit, but I think we are, as the pandemic is dying down, we're now sort of getting back to the mission, and hopefully this will continue through clinical trials. So I'm going to stop very soon here. The near horizons, right? So right now, I just wanted to leave you with the understanding that these types of advancements, will not happen, may not happen for another generation, and it is incredibly exciting and an honor for somebody like me to just wander in. When I went into oncology, melanoma, renal cell carcinoma, these were death sentences, right? And it is just amazing how much response is happening now. And in fact, if there is any silver lining from the pandemic, it is in times of need, we come together and we rapidly advance the science to meet the challenges. And that is something that our country, as well as many others throughout the world, are able to do. And it is just an amazing time, because a lot of this is going to get repurposed into our mission for women's health and cancer. A genome can be sequenced in 1 to 2 days, vaccines produced in weeks. The personalized cancer vaccines that I've showed you were produced in a week and a half, okay, so very quick. Tremendous potential for patient society in our country. And acknowledgements, this is my research group here. This was an event at the Cleveland Zoo. So if you're ever up there from Dallas, it's a wonderful opportunity. It was the Asian Lantern Festival. I thought, wow, this would be interesting. Asian Lantern Festival in Cleveland. Okay, so let's go ahead and check it out. Why not? Well, let's invite everybody over. We had a break from the masks at the time because it was outside. Got to see all the animals and everything, but it was a wonderful, wonderful event. And of course, thank you for your engagement and support. We are all in this together. I want to point out that while the government and NIH does a wonderful job, it is the grassroots and community engagement that really drives the education, the access, and the excitement. This is a story that I will say is that the very first human genome was sequenced with philanthropic dollars. Okay, so a lot of people don't know that, and it is a fact. And the very first immunotherapies were developed just because somebody had an idea, and look how much better we are for it. So thank you very much for your attention, and it's wonderful to be here.